Hello and welcome. My name is Michał Palczewski. I'm a student at Gdańsk University of Technology, and I'll tell you a few words about braids. The oldest known depiction of hair braiding may be around 30,000 years old. The Venus of Willendorf, also known as the Woman of Willendorf, is a female figurine that was estimated to be made between around 28,000 and 25,000 BC. It is disputed whether she was braided hair or some kind of a braided basket on her head. Although braids were known so long ago, mathematical research on braids is much newer. It is a rare case in mathematics that it is possible to determine the exact moment when a mathematical theory arose. Officially, one can actually say that such a case was Emil Artin's Theorie der Zöpfe, written in 1925. However, as Moritz Appel points out, Artin, while officially the sole author of the article, worked on the topic with Otto Schreier. Moreover, mathematical research on braids could be discovered in the 1890s thanks to Adolf Hurwitz. He studied the braids created by the movement of branching points on the Riemann surface. Appel also points out that Gauss also considered braids in an unpublished note from around 1825. What is unique about Artin's behavior is not only his attempt to study the braids as a mathematical object independent of other objects, such as Riemann surfaces, but also his attempt to obtain a complete algebraic formalization of the set of braids. He himself spoke of his research on the braid theory as early as 1926 as topologically misguided, auf topologischen Abwege. But when Artin was working on the braids, his purpose was clearly to arithmetize, that is to represent the braids using the group theory and research the relationships within the group of braids and their transformations. In this sense, Artin's work can be considered the first attempt to formalize braids. In everyday life, we see braids very often, in hairdressing, in jewelry, in robes, bread, cheese and many other items. But what is a braid in mathematics? Let's pick some points. We create a copy of them. We begin to draw strands connecting the selected points. The strands flow from left to right. They cannot turn back. They can, however, be intertwined, but not going through the same point. Crossing is not allowed. Draw the strands until all the points are connected. Thus, we get a braid. A braid with n strands is a plot of n continuous functions defined on a certain closed interval AB. Functions f1, f2 until fn, satisfying two conditions. Their graphs do not intersect, so for each t in the interval AB, we have the functions fa and fj not equal for different a and j. The sets of their values at the beginning and the end of the interval are the same. More formally, there is such a permutation tau for the set of natural numbers from 1 to n that fi on b is equal to f tau I on a for a from 1 to n. We will denote the braids with a lowercase letter without an index. Now we will say when two braids are considered to be the same, equivalent. Let us first consider two simple cases. Shift. The braid G is defined on the interval a plus c, b plus c, and its graph is like that of a braid F, only shifted to the left or right, so it's easy to say that they're the same. The braid G is defined on the interval a divided by c, b divided by c, and it's braided similar to F, but more densely if C is greater than 1, or less frequently if C is less than 1. Here we are also able to say that it's the same braid. In general, we consider braids to be equivalent if there is an isotopy between them. What is it? If the fi functions are defined on an interval AB and gi are defined on an interval DE, the isotopy connecting them will be continuous functions of two variables. The functions are denoted by uppercase F with an index and are defined on a trapezoid whose lower and upper base are given on the slide. And those functions have to fulfill the following condition. For each fixed S, functions form a braid where uppercase Fi in the point 2, 0 is equal to lowercase Fi in T and uppercase Fi in T1 is equal to Gi in T. The isotopy is thus a continuous family of braids joining a braid F with a braid G. Intuitively, if the braids aren't too tight or too long, then you can grab the left ends of the braid with your left hand and the right ends of the braid with your right hand and shake it. If the braids are equivalent, then when shaken, they should look identical. Now, knowing what is braid isotopy, we can check if it is an equivalence relation. Isotopy of braids is reflexive because a braid can be turned into itself without transforming it at all. Symmetric because if we transform one braid into another, then repeating the transformation from the end, we will get the first braid from the second one. Isotopy of braids is also transitive because if a braid can be transformed into another and the second one into the third, then we can perceive two transformations as one and thus turn the first braid into the third one. The first thing we pay attention to is that we can compose two braids. It simply means placing them one by one and connecting the threads. So, if the braid F is defined on the set AB and the braid G is defined on the interval BC, then the set of threads ends of the first braid coincides with the set of beginnings of the threads of the second braid, so they can be properly joined and obtained new braid F composed with G. The operation defined in this way is cumulative. This is directly due to how composing braids works. We don't even need to consider any braids. Let's look at the rectangles. If we compose A and B and then glue C to the right side, we're gonna get exactly the same braid as if we glued B to C and then added A from the left side. Moreover, it's not difficult to show that the operation of combining the braids is determined and cumulative on the equivalence classes of the braids. Its identity element is the constant braid, or rather its equivalence class. Is there an inverse of a braid? Let's look at the mirror image of a braid. We can compose a braid and its reflection in two ways. First, the original braid, then the reflection, or vice versa. First the reflection, then the original braid. As we can see, in both cases, we'll get an identical braid. Generally, the braid opposite to the braid F is obtained by mirroring the braid F symmetrically with respect to the OYZ plane. And what about commutativity? Here's an example. We add two braids in the two possible ways. Results may vary. Look at the red thread in the top picture, it starts at the bottom, and below it, the blue one, starts at the top. So these braids cannot be the same. This means that the operation of composing braids is not commutative. Thus, we have shown that the classes of equivalence of the braids are a group due to the operation of composing braids. We call this group the braid group with n strands and denoted by B with an index n. Consider any braid and its projection onto the OXZ plane. We say that two strands cross if their projections on the OXZ plane intersect. It may happen that the projections of the three strands meet at one point, or that the projections of two strands coincide for a certain distance. But after isotopy, shaking, we can assume that the number of crossing is finite. Only two strands cross in a crossing, and each crossing has a different x coordinate. Then, either there are no intersections and the braid is trivial, or you can divide the interval AB into short intervals so that there is only one intersection in each of them. This means that any braid is a combination of braids in the form sigma I and sigma I inverted presented in the picture. In other words, braids sigma I for I from 1 to n-1 are generators of the group of braids Bn. Following relationships are true between these generators. It turns out that all relations between generators result from these two relations. This claim was proved independently by Artin in Theory of Braids and Bohnenblust in the Algebraical Braid Group, both in 1947 in Annals of Mathematics. By loosening the strands, we are able to divide the braid into such segments in which there is only one crossing of the strands, and such a crossing will correspond to a specific elementary braid. However, such a notation is ambiguous. Now, let's take a look at this braid. Will the braid change a lot if instead of first crossing the yellow and the green strand, we first start with the blue and the red one? Given the flexibility and ductility, the change will not be significant. Likewise, at the end of the braid, the black-blue and green-red crossings are independent and can be legally interchanged. So the question arises, how to check when two braids are the same and how different words can describe the same braid? This problem is solved by the theorem constructed by Artin and Magnus, which distinguishes three types of ambiguities of the writing of the braids in the form of words. First, as we already know, composing two elementary braids together is equivalent to a trivial braid. If in two different elementary braids, that is such that the absolute value of I minus j is not less than 1, then the braid sigma I, sigma j is equal to the braid sigma j, sigma I. To illustrate this, let's take a moment to look at how such two braids would look like. 3. When the crossings in the two elementary braids have one common strand, that is, j is equal to I plus minus 1, then the sigma I, sigma I and sigma j are equivalent. We can see it in the picture. Although this notation seems to be more convenient at first glance, there are some difficulties with it. The problem is that the Artin-Magnus theorem does not give us the tools that could allow for an algorithmic determination of whether two words encode the same braid. We can also look at the braids as permutations. For example, in the given figure, the first of the braids induces the permutations below it, and the same with the other one. Note also that the permutation induced by the composition of the braids is the composition of the respective permutation. Although we connect the braids by gluing them together, as you know, the permutation composition is read from right to the left, so you have to write the permutations in the reverse order than the braids. Thank you for your attention, even though I presented just the tip of the iceberg, which is the braid theory. I hope it was interesting.